Hello and welcome to the fourth and final in a series of special programmes live from the British Science Festival in Aberdeen. I'm Chris Smith and I'm joined today by Andy Holding. Hi Andy. And also Martha Henriques.
And we'll find out how the British Antarctic Survey intend to drill down into subglacial Lake Ellsworth to investigate one of the most challenging environments on Earth.
Thank you, Martha. That's all coming up. So if you would like to take part in the programme, you can tweet at Naked Scientists. You can also comment on facebook.com/thenakedscientists, or you can email chris@thenakedscientists.com. Very soon, we'll find out what it takes to drill through 3 kilometres of ice while working under very harsh conditions. But first, Martha, tell us about your highlights of today.
Well, I spoke to Tom Manley, who's a clinical neuropsychologist at the MRC Cognition and Brain Sciences Unit, and he's been looking at unilateral spatial neglect. This is a condition which affects a large proportion of stroke sufferers, and it results in them being unable to be conscious of information from either their right or left-hand side, depending on which side of the brain was damaged.
It really is a sort of through-the-looking-glass style phenomenon where you get these very interesting effects. So some people do literally divide the world in two and ignore everything on the left. Other people seem to, it varies enormously, so they have a sort of gradient that they'll be most aware of things on the right and then increasingly less aware of things as they move towards the left. But there's this very strange thing where people seem to divide the world up into left and right. For example, if they were asked to draw a tree and a house and a person, they would draw the right side of the person, then the right side of the house, then the right side of the tree, even though one of these objects is to the left of the other. It's like they're breaking the world up into an attended segment of interest, and whatever that is, whatever coordinates that has, will then get divided.
Now, Manley and his colleagues are going to look at the mechanism behind this phenomenon and how best to treat stroke sufferers to regain access to this information.
Martha, thank you. Well, for me, a highlight today was actually having a government minister in the building. David Willetts was here to discuss the concept of open access publishing. There's going to be some quite big movements in this direction. Do you know about open access, Andy? Do you know what that is?
Yes, so this is when you don't have to pay to read the journal, where at the moment you have to pay these extraordinarily high fees to get access to some of the biggest papers.
Yeah, so if you, for instance, want to access a paper in a journal like Nature, then you either have to pay a subscription to it or you have to buy access to that individual paper. Now, in recent years, a number of people have come along and said, actually, the world of publishing would be much better if we were to publish things in what's called an open access format. The idea here is that rather than having to pay to see the papers, everybody can see them online, live from the moment of publication. And instead, the costs of publication are transferred from the consumers to the people doing the publishing. So if you were to publish a paper in, say, PLOS One, Public Library of Science, then this would attract a fee from you to publish there, but then everyone in the world has access to it. And people are arguing that this makes the world of science publishing much better because immediately the science is visible to all and it will accelerate collaborations and it will also accelerate the process of doing research in all countries in the world. And what David Willetts is saying is that the UK government is going to pump some money in the order of about 30 million quid. We think that works out at about £2,000 per paper that's going to be published to make all of the research being published, even in top-tier journals like Nature, free for everybody. I don't know what you think about that. I have some reservations. What do you think?
I think it's a good start. It's better than the system we had before, but that is a huge cost to the taxpayer, and you have to wonder, why can't we just make this free for other routes? Why do we have to pass that cost on to the taxpayer who are already paying for science?
I agree, and I actually asked them that. And my concern here is that the UK taxpayer is effectively funding journal subscriptions for people in other countries, which I think is a rather strange way to do this, because at the end of the day, why are we giving to other countries free access to our science? Why don't we just make it free for British scientists? The argument, the counterpoint is, well, this might be fostering relations with other countries, but actually other countries tend to want to sell us their science, so it doesn't seem like a two-way street. And I put this to David Willetts, and he said, well, I think actually there is some benefit to being amongst the first to do something, and by being up front, it hopefully will turn out to be advantageous for the country in the future.
He might be right there. He might be pushing onto something, a future where there's more open access from around the world.
Thank you, Andrew. An expedition to tap into a lake buried 3 kilometres beneath the Antarctic ice sheet kicks off next month after 16 years of planning. Scientists will be looking for the chemical hallmarks of life, as well as bacteria and other microbes in the lake water, which has been cut off from the outside world for conservatively 10,000 or more years. Chris Hill from the British Antarctic Survey has the unenviable task of being in charge of the operation and actually drilling into the lake. So first, Chris, set the scene for us. What is Lake Ellsworth and what are the conditions like there?
Lake Ellsworth is a liquid body of water underneath approximately 3.2 kilometres of ice sheet. It's a fairly sizable lake. It's probably about the size of Lake Windermere, and it's been cut off for, as you say, many tens or possibly hundreds of thousands of years from our biosphere. The basic premise is that where there's water, there's life. We see that all over our planet, and there's a very special relationship between water and life. But because of the extreme conditions of Lake Ellsworth, the dark, the high pressure, the apparent lack of energy transfer, we really wonder what that life might look like. It's a fascinating exploration to find something new.
What keeps it as water under all the ice?
Well, that's a very good question, and it's actually quite an easy answer. The Earth is relatively quite a hot body. There's a lot of geothermal heating effects underneath the Earth, and ice, for all it's cold, is actually quite a good insulator. So if you get a thick enough layer of ice over a hot body, it's inevitable that you're going to get pockets of water.
And we think that water's been there for a very long time.
Yeah, again, it's quite difficult to say until we can actually access the lake and get a sediment core to find out when that ice sheet last collapsed. But the hypothesis is it's many hundreds of thousands of years, possibly as many as 1 million.
Wow, that's quite some time, isn't it? What about on the surface? What are the conditions that you've got to work in like? What's it like up there?
It's not pleasant. We're on the top of a very open ice plateau. It's very cold, so even in the middle of summer, we're looking at temperatures of minus 25 degrees Celsius with average wind speeds of 25 knots. So it's not pleasant. There's no shelter. There's nothing anywhere near us for about 200 kilometres. There's no mountains. So we really are exposed. We have to take everything in. There's nothing there already, so we have to take all our equipment in, but all our living accommodation and everything with us. We'll be living in tents, and we'll be wearing probably the thickest clothing you've ever seen.
Michelin Man positive.
Completely.
So how will you access the water in the lake? Because it's under 3 kilometres of ice. It's a long way down.
That's right. There's many ways we could do this. There's a lot of techniques for drilling into ice, and scientists have been doing this for many years. But by far the cleanest and quickest is hot water drilling. And essentially, it's the same as a jet wash that you might use on your car. We're going to take some water from the melted snow, the ice on the surface, and we're going to heat it, and we're going to clean it, and then we're going to pump it up to a very high pressure and push it through a very long hose. And it's a very quick and efficient and very clean way of drilling.
So this will start at the surface and slowly melt its way down towards the lake?
Exactly, and not so slowly, actually. 3.2 kilometres, we will probably get through from the surface to the lake in about 60 hours, so
Really?
2.5 days.
And you've got a 3 kilometre long hose pipe?
We've got 3.5 kilometres. and that's another interesting thing, actually, because the number of engineering challenges we've faced to get this far are huge, and even simple things like you wouldn't think it would be difficult to get a 3.5 kilometre hose made. It actually is. We only found 2 companies in the world that could produce a hose to our specification. So, I mean, just the hose itself, just a simple piece of tubing, was a real phenomenal engineering achievement.
So the hot water goes down the hose, this melts the ice in front of it. Mm-hmm. How do you stop introducing the very molecules that you're going to go hunting for in the lake into the lake by dissolving them out of the ice and pushing them in at this very high temperature?
Yeah, that's quite a good question. The preservation of the lake has been paramount in our minds right from day one for 2 reasons. One, obviously, we have an environmental responsibility to keep the lake pristine. But probably more selfishly, we actually want to preserve our samples. We don't want to be measuring anything that we've put into the lake accidentally. So it's twofold. Firstly, the water we're using to drill is taken from the background ice. So there's nothing that we're going to use that wouldn't come into contact with the lake at some point anyway. But more than that, the drill has been designed so that as we fire hot water out of the nozzle, the actual melted ice that's in the way will actually flush back up the borehole to the surface, keeping it away from the lake. So the only water that will actually reach the lake in the end is the water that's already gone through our filtration system and has been pumped down at high pressure.
So you're filtering all the water that you're using for the melting?
Absolutely. Every stage of this program has a cleaning protocol, and for the water we filter to beyond pharmaceutical levels.
So that means screening out bugs and things like that?
Completely.
So how will you know when you've actually got through the last bit of slush and you're now in the lake?
It's a good question again. There's two ways. We'll know when we're close because the radio echo sound and seismic data has given us a really accurate distance to the surface of the lake. And we obviously will know how much hose we've paid out, and we will know the stretch of that hose. So we'll know when we're within a few metres. But then what we have is a suite of pressure sensors that will allow us to monitor the change in water levels at the top of the borehole. So we anticipate that as we break through to the lake, we won't fully have accurately equalise the pressure of the lake. So as soon as we do break through, there'll be a pressure change in the borehole, and we'll be able to sense that, and that will give us the indication.
But like the Coke bottle, when you take the top off and it fizzes up a bit, you'll see a little pressure change.
Yeah, definitely. We'll see a pressure change, and we should be able to measure that, and that will be our accurate indication that we've broken through.
And then you'll drop in some probes to measure things in the lake.
That's exactly right. So when we finish drilling, we need to recover the drill hose because we can't put two things down the borehole at the same time. So we recover the drill hose. And then because we're not using any antifreeze to keep the hole open, we have just 24 hours to deploy two instruments. The first instrument is a sampling probe, which will take water samples and will also flush through some of the background filtrate in the lake, and will take a small amount of mud from the bottom of the lake. We then recover that, and we deploy a sediment corer, which we hope to get a 3-metre core of sediment from the base of the lake, which will give us a really good time record of what's happened in the West Antarctic ice sheet in years gone by.
Chris, thank you very much, and good luck in October. That's Chris Hill. He is from the British Antarctic Survey in Cambridge. Martha.
Well, now from one polar region to the other, today I spoke with Kate Britton at the University of Aberdeen, who's been excavating a prehistoric indigenous Arctic settlement in West Alaska called Nunalak. Britton and her colleagues found thousands of man-made artefacts from this abandoned settlement that were preserved in the permafrost. Now, because of climate change, the permafrost is melting and releasing this settlement for archaeologists to study. Perhaps the most interesting preserved remains are an unprecedented number of human hair samples from around 50 individuals. Britton told me how she is analysing these samples to find out about the people who lived in Nunalak.
So the method I use is called stable isotope analysis, and we're measuring isotopes of carbon and nitrogen. So isotopes are sort of different versions of individual elements. So we're looking at the ratio of carbon 12 and 13 and nitrogen 14 and 15. And these different isotopes have different masses, if you like, and that causes them to behave slightly differently in different parts of the ecosystem. And certain parts of the ecosystem can have particular isotopic signals. So, for example, we can use carbon isotopes to differentiate between marine and terrestrial ecosystems, because the source of carbon in terrestrial ecosystems is atmospheric carbon, and the source in marine ecosystems is dissolved in organic carbon, which have very different isotope signatures. Those signatures pass into the primary producers within those ecosystems and then up into animals and eventually into humans. Nitrogen works under a different mechanism. Here we're looking at something called trophic level enrichment, which affects the nitrogen isotope signature up the food chain. Basically, with every step up the food chain, you have an enrichment, and that can allow you to pinpoint the types of animals people were eating. And if you combine those two methods, the carbon and the nitrogen together, you get an idea of whether the resources were marine or terrestrial, and then also the trophic level of resources. So, for example, a terrestrial herbivore would have very low nitrogen and more negative carbon, and a marine mammal, which is obviously the top of the food chain in the ocean, would have very high nitrogen and more positive carbon.
These isotope signatures can tell archaeologists about the diets of Nunalak's inhabitants and how much or little these diets varied seasonally.
So what we can do is not just take a section of hair, but also subsample that hair and look at variations in the stable isotope signature, in the stable isotopes of carbon and nitrogen, all the way down the hair, and to see whether there's any evidence for seasonal resource use. And obviously we're dealing with an area that's very seasonally bioproductive in the sense that you have lots of resources available for short periods of time. I mean, sort of traditionally, there's this idea that that kind of environment would be very, very difficult to live in, that you would have seasonal food shortages or so. But actually what we've found, preliminary evidence suggests that actually, if you look at the hair growth and the changes in isotope data through the hair, there actually aren't very many, which is very interesting. That seems to tell us that they not only had a more of a mixed diet incorporating terrestrial and marine resources, so things like salmon and caribou and even marine mammals, but that they were eating seasonally available resources throughout the year. And of course, that tells us a lot about things like storage and seasonal provisioning, and really is testament to the amazing Arctic adaptations these groups had.
That was Kate Britton at the University of Aberdeen, and she's also working on this with the Max Planck Institute of Evolutionary Anthropology.
Martha, thank you very much. Now, we've all been there. It's the end of a long day, you're tired and you're hungry. You know you shouldn't, but you're finding the lure of the cake counter is proving hard to resist. Scientists think that this sort of willpower failure is responsible for many of us putting on weight, but thankfully Aberdeen psychologist Julia Allen may be able to come to the rescue.
What we were particularly interested in is why people don't stick to their good dietary intentions. So we know that a lot of health promotion campaigns focus around giving people information under the assumption that if you give people more information, they'll make a better choice. So an example would be the 5 a day campaign. We're telling people you should eat 5 a day, we're telling people the benefits of 5 a day, and we're assuming at some level that having that information will make them more likely to eat 5 a day. But unfortunately what we know and what's now very well established is that information on its own isn't sufficient to produce behaviour change. So we've been developing little signs to be displayed at food order points in coffee shops, and the signs show the entire range of snack foods that are available, ordered from, on the left-hand side, the least calorific up to the most calorific on the right-hand side. And they have a little message at the top saying, if you want to eat fewer calories today, then choose one of the snacks on the left. And so we're directing people's attention away from the higher calorie snacks and towards the lower calorie ones.
There'd be sort of Mars bar over on the right, banana on the left, and so you're saying to people, you can have one of those or one of those, and if you want fewer calories, go to the left-hand end of the scale.
Yes, and we're trying to capitalise on people's there's naturally a slight bias for the left side of visual space, so people will naturally pay slightly more attention to things presented on the left than the right.
Does it work?
When we've been testing these, we randomly allocate coffee shops in blocks of a week. So we'll have the sign randomly displayed for 6 weeks out of a 12-week period, and then we'll record sales figures throughout the entire period and compare sales of all the different items when the signs are there and when the signs are not. And what we're seeing is that when the signs are present, we see a measurable reduction in sales of all of the higher calorie items, and about half of the lower calorie items increase their sales. So people do seem to be switching down and making different dietary decisions.
So it clearly works because people were changing their behaviour. How did it go down with the store owners, though? Because if they're not selling a Mars bar and they're selling an apple instead, that's okay. But if they sell no Mars bar and someone doesn't buy something instead, they're going to lose money.
I think that's always a tricky issue, and we did have a lot of negotiations at the start of this project about whether or not we could trial an intervention that ultimately might negatively impact on their sales. But I think there's been a real shift in the culture of organisations towards promoting healthy eating, so many of these places now have a healthy living award and so on. So they were actually fairly open to the idea. The beauty of this intervention is more typically people were switching one purchase for another. So some people certainly didn't buy things, but a more typical pattern was to see how many calories were in, for example, a latte, and to choose to have a black coffee instead.
Did you quiz any customers who had interacted with the sign and then bought something so that you could see how they reacted to it? What was their perspective?
Yes, we did. We had about 130 customers who agreed to come and be interviewed after the study, and we went away and we measured their executive function, and we found that the people with the weakest executive function were much more likely than others to have changed their behaviour in response to the sign. People were buying fewer calories than they would typically buy in a visit to that coffee shop. And when we asked them how they'd used the sign, most had used it in the way that we'd expected or had not used it at all, had either not noticed it or not felt it wasn't relevant. But we did have a sizable minority who used the sign in a way where we hadn't anticipated. So they would see, for example, that there was 300 calories in their milky coffee and decide that they could have 3 Milky Ways instead of that, and that's exactly what they did. So,
So they were buying stuff which was actually not necessarily a healthier option, but they knew they could get away with as many bad things as one coffee, so they were trading one evil for another.
yes, there was a sizable minority did exactly that, and I have to say, anecdotally, they were all women. So they made the decision based on, it seemed to us, that, oh, well, I would have had that anyway, and look, I could have 3 small bars of chocolate for the cost of that coffee, which was not really what we intended, so it's a work in progress.
Will this translate to other things? You've done it with food. What about fizzy drinks or maybe other things? Could it work with cigarettes? Could you have nicotine and tar levels or something on a similar sort of scale and persuade people to switch to a less unhealthy cigarette?
Well, we've done it initially in snack foods, and we've also done it in drinks, because we know that the kind of premium coffee industry is also a big source of calories. So I think a lot of people don't realise when they're in Starbucks that there's up to a 500 calorie difference between a full fat hot chocolate and a black coffee. And so we've got the same effect in drinks, but it's a general principle. So in theory, it should apply to any behaviour that requires willpower or self-regulation.
Julia Allen, and the results show that people tended to eat, on average, 66 fewer calories as a result of this intervention, and that is sufficient, other studies have shown, to make a meaningful dent in a person's likelihood of gaining weight. Now, apart from occasional lapses in willpower, there might also be another reason why an overweight person struggles to keep weight off in the long term, and that's even if they diet successfully in the shorter term. High-fat foods, scientists are finding, could be damaging a region of the brain called the hypothalamus, which is concerned with controlling energy balance and food intake. This, Aberdeen researcher Linda Williams suspects, might make people more prone to future overeating. Hello, Linda.
Hello.
So how did you actually do this study?
Well, what we did was we used a strain of mice that's very susceptible to gaining weight, and we put half of the mice on a high-fat diet and half of the mice we kept on a low-fat diet.
What's a high-fat diet?
It's a diet that contains about 60% of the energy in the form of saturated fat, so not healthy diet, I must say.
Unhealthy even by Scottish Glaswegian standards.
Absolutely.
I'd go as far as that. So, I mean, a normal, for comparison, human high-fat diet, well, a normal diet would contain, roughly a 30% or a third of the calories should come from fat.
We eat a lot more fat than a mouse, so this was a big dietary shock to the mouse.
And what happened?
Well, I must say that although it's a dietary shock, the mice love this diet. And so after a couple of days on this diet, we looked at the hypothalamus of the two groups of mice using 2 techniques, transcriptomics, where we can look at thousands of genes at the same time, and proteomics, where we can look at thousands of proteins. And we were very surprised by the changes that we saw, because a lot of the genes and the proteins that were changed were actually associated with ischemia, which is a lack of blood supply, and also with infection and inflammation.
Is this specifically in the hypothalamus, or are other bits of the brain vulnerable too?
Well, we followed up some of the gene changes using a technique called in situ hybridization, where you can actually visualize the whole of the brain, and we found it was mainly located in the hypothalamus.
Obviously, that's important because the hypothalamus does control energy balance. It controls metabolism and feeding behaviour. Yeah. So would your deduction then be that if you have a high-fat diet and you get this damage to the hypothalamus, this makes you more prone to overindulge in future?
It would seem that way, because in the hypothalamus there are 2 groups of neurons, one that makes you eat, one group that make you eat, and one group that stops you eating. And it's the balance between the signals from these neurons and the way they communicate with one another. And we think what's happening is the communication between these 2 groups of neurons is compromised on a high-fat diet.
So if you take the mice that have had the high-fat diet and now manifest these changes in their brains and then offer them normal food, do they overeat afterwards compared with mice that haven't had the high-fat diet?
We haven't done that experiment, but I believe that they would overeat. But they'll be limited by the amount of food they can physically eat.
Okay. Is this a permanent change?
We really don't know at the moment, but we've got a project starting in the autumn where we'll be looking at this, because obviously we need to see where it's reversible. I would imagine if you eat a high-fat snack, which we all do from time to time, you might get a blip, a change in these genes, but you'll recover quickly. The problem is when you eat a high-fat diet all of the time, then these changes may become permanent and would obviously exacerbate obesity.
What about people who have a preponderance to having high levels of fat in their bloodstream because of a metabolic problem, like, say, diabetes or certain thyroid disorders or other hormone disturbances? Do they also mean that they could be at risk of developing these problems?
I honestly don't know, but it's really a good question and worth looking at.
And what about the relevance of the mice to humans? Because obviously, mice diets are not something we generally get too worried about, but we do worry about human health. So can we compare one with the other?
Well, obviously, the outcome of this work is to look at obesity in humans. The hypothalamus is what's called an ancient part of the brain, so it hasn't evolved a great deal in different species. That's why we can use mice as good models for obesity. So yes, I think it's relevant to humans, and I'd be very interested to take these studies further, to do brain imaging studies in humans on a high-fat diet.
What about the long-term consequences then? If we do, or if your research does suggest that there is this consequence, what does that mean we ought to do in terms of intervention to stop people damaging their brains in this way?
Well, I think the thing is we just have to adhere to the dietary guidelines that are there at present, which is we can all indulge in high-fat food, tasty snacks now and again, but just don't overdo it.
But that clearly doesn't work.
It
doesn't for me.
No, it doesn't work for some people. And obviously, by looking at these mechanisms in the brain, we hope to identify targets that we can use, to develop drugs to hopefully help people who want to lose weight.
But not only lose weight, prevent the damage in the first place. So will we be buying chocolate bars and cream cakes that have chemicals in them to stop your brain decaying at the same time?
That's a great idea, but I really don't think so.
Linda, thank you very much. Linda
Thank
Williams
you.
from the University of Aberdeen. That's it from our roundup of the best of the Fest, the British Science Association Festival, from us here at the University of Aberdeen. We'll publish more of these interviews on our full Naked Scientist programme on Sunday. But thank you very much for joining us, and thank you, Ben Valsler, for producing today's show. Until next time, goodbye.